In chapter 4, we're going to be talking about projectile motion. And projectile motion is essentially, it's an example of two-dimensional motion. So we want to use kinematics to describe two-dimensional motion. And when we do that, the first thing that we should do right away is that we should define what is a projectile. Okay, so the simple question to start off with is, what is a projectile? I mean, of course I don't have to tell you what it is. You already know it. But what's the language of physics here? What a projectile is in the language of physics, it's an object in free fall with a non-zero horizontal speed. That's how you define what a projectile is. And what you're going to see here is that because we're dealing with two-dimensional motion, we're going to have our x direction and our y direction. There's another two-dimensional motion that we'll talk about called circular motion, but we won't do that till chapter 6. So let's go look at this here. So an example of two-dimensional motion goes like, right, is projectile motion. And so if I talk about two-dimensional motion, let's be a little bit more explicit. So what you're finding here is that projectile motion is a very odd and super cool topic because there is literally an X motion and there's literally a Y motion. And what we say here is that these two motions, these motions are separable. So mathematically, these two motions are separable. And that is a really strange thing. And the only way we could explain why these motions are separable is that we'd have to come in and really look at Newton's second law and just look at the mathematical equations, which are differential equations. But this is what we find here, is that when we, so from Newton's laws, what you find here is that we have something called its position, its displacement vector is typically written R. And when you get the solution to this trajectory, that means you have a solution to this type of motion, what you find here is that the solution for X and Y, you literally get that I can separate the X motion from the Y motion. In other words, one-dimensional problems, which is something we can solve, in two-dimensional motions, we get two one-dimensional problems, which means that we can immediately apply everything from chapter 2. So in other words, what happens here is that this allows One, to have two-dimensional motion. As two one-dimensional problems. But guess what? We know how to solve one-dimensional problems. This is what we solved in chapter 2. Okay, this is what we solved in chapter 2. So what happens now is that because we have two-dimensional motion, that means all of our kinematic variables are now two-dimensional. So what this is saying here is that all of our kinematic variables are now two-dimensional. That means we must use vector ideas to get variables. What do I mean by that? Well, let's think about velocity. So if I think about velocity, velocity is now a two-dimensional variable. So if I write the word velocity, what this really means is that I have what? I have a Vx and I have a Vy. So how do I express this? Well, we know how to express Vx, but what this tells us here is that if I talk about velocity, I must talk about two things. I need to talk about its magnitude and its direction. How do we calculate these things? Well, we know that the magnitude must be the sum of the squares of the Vx squared plus Vy squared square root. And we know that how we get the angle here must be Vy over Vx. So any variable that we talk about in two-dimensional motion is now two-dimensional. And so we have to use the vector ideas from the previous chapter. So this tells us then all of the kinematic equations now are doubled. So the kinematic equations are now doubled. That means I have a set of equations for x's and I have a set of equations for y's. But there's a simplification, and it turns out to be a very important simplification. The important piece here is the accelerations are unique for projectile motion. And what you find here is that when you look at the x acceleration, there is none in free fall motion. And this guy, this greatly reduces the x equations down to one equation. Okay, one equation. And what's that one equation? It turns out to be this guy. There's only one equation for the x equations. On the other hand, AY, because you're in free fall, is minus G here. So what you get here in this situation is you get the full kinematic equation. And you know that full kinematic equations is because that's what you're seeing in what we did in chapter 2. So we started talking about projectile motion. And when I talk about projectile motion here, what you're seeing here is that this is what we talked about last time. So what you're finding here is that we said, what is a projectile? And what I said a projectile is an object in free fall with a non-zero horizontal speed. So since we're talking about two-dimensional motion, that means in this case, it's going to be X and Y. It turns out that mathematically, there's two separate motions. And when we say there's two separate motions, we call this separable, and it's really a mathematical expression. And what I mean by that is that when you look at Newton's laws, that is, these are the governing laws of all of mechanics, and in this case of projectiles, the solution to these laws gives you a two-dimensional displacement function. So if I call my displacement function R, it has an X and a Y component. And if these two solutions are separable, that means I can get all of the X pieces into one function, which I call big X, and I can get all of the Y pieces into one big function called big Y, let's say. And these two are completely independent of each other. And so there's this really strange thing that when you do that, you literally are taking a two-dimensional, I should be careful, I'm taking one two-dimensional problem, and it's now two one-dimensional problems. And that's one of the main reasons why we solve this in Physics 4a. If this was not the case, we would have to be in a upper division mechanics course to actually solve this thing. But wait a minute, we know how to solve one-dimensional problems. We just did that in chapter 2. So what we do now is that we have to get the vector ideas now. Because if I have a two-dimensional problem, that means there's a vector part for the velocity. So if I look at the velocity, I then go to my x motion equations, and I get my Vx. And then I go to my y equations, and I get my Vy. And then to really get the velocity in 2 dimensions, then I use the vector ideas to get the magnitude and the direction here. So as I was saying here is that there's really two motions. So if I have two motions, I have my x equations and I have my y equations. But Newton's laws tells us that there's a really important piece. And because of their separable, the acceleration in the x direction and the acceleration in the y direction are two different pieces. But here's the beauty. The acceleration in the x direction is 0. That greatly simplifies the x equations. So instead of taking our 3 or 4 equations, it really comes down to really one equation. Well, if I have 0x acceleration, then clearly the velocities cannot change. Right? Just to make sure that this is x. Velocity never changes. Of course, there's no acceleration. But when you look at all of the equations, the position only has one equation. That the position in the x direction is just the velocity times the time. But if I look at the y equations, what you're seeing here is that you get what? You get the full free body, free fall equations that we've been studying. So you get the whole equations that we used in the kinematics table here. So what I want to do here is that I want to go in and I want to start to really look at this thing here. Okay. And so it's sort of like in summary, what am I really saying here? Okay, and this is what I'm saying. Because these equations are separable. And remember, this is really a mathematical equation. And what this tells me here is that I have some position function in 2 dimensions, and I'm able to isolate these 2 pieces here. So what this really tells us here is that these two, that they're completely independent of each other. So mathematically, they're telling us that we can isolate X and only focus on X in 1 dimension. I can isolate Y and only focus on Y. So my job here is to then do what? I now want to interpret. Right? I want to interpret this independence of the components. And so I want to say, what does this really mean? Okay, what does this really mean? So what I want to do here is that I want to go in and draw some pictures. So what do I know? The X motion has AX equal to 0. So this implies here that if I had a ball rolling on a table at constant Vx speed. So when I think about this thing picture-wise, what do I mean by this? So you could imagine that I have a ball, and let's say that the ball is doing this type of thing, right? It's moving at constant speed. So I'm looking at this thing here, and it's just moving at constant speed. So when I look at its speed here, I'm getting a constant horizontal speed. So that means if I start my clock here, then any time afterwards, the speed is exactly the same. So it's like a ball rolling on a table here. But we also know that the Y motion has a Y equal to minus G. So this is like a ball in free fall. So in this case here, you could imagine here that I have the following scenario here. So I have a red ball. And then what I know about the red ball, if it's in free fall, it has to be getting what? Faster and faster and faster and faster. So when I'm looking at the situation here, we could come in here and we could just say, yep, here's my speed Vy. Oops. And then I'm getting faster. I'm getting faster. Where initially, in this case, Vy was 0 to start off with, because I'm just imagining that I'm just dropping a ball. So what we say then is that in projectile motion, we have 2 one-dimensional problems that are superpositioned. So I'm saying here is that in projectile motion, we have what? 2 one-dimensional problems that are superpositioned. And when we say superposition, what this means here is that we overlap these motions, right? They add, as we would say. And so what this means here is that then picture-wise, what we do here is that we can get this curved or parabolic trajectory using superposition. And what I mean by that is that let's set up a table. So I can imagine that I have a table. And I hope this table is high enough, but here's my table. And what we're going to do here is that we imagine that the ball is falling off this table. So I have a ball that's rolling, okay? And let's say that, you know what, I'm actually going to start the ball over here because I want the ball to be right here. So I'm going to go here, here, here. And so when you're looking at this, I have a ball that's moving. And as it's moving across this table, we're going to say that it's sliding at constant velocity. So that means its velocity vectors are going like this. And then there's the moment that it goes off the table here. So the moment that it goes off the table, what we know here is that I have two one-dimensional problems. So there's a problem here where this thing is moving at constant velocity along the x direction. So here's one of my motions, which is continuing to move like this. But now there's a second motion. And the second motion is doing what? The ball is falling vertically. So what I'm seeing here is that it's falling here, and it's getting farther apart. So I got 1, 2. So then I'm going to have one more here. And so what you're seeing here is that now I have a ball speeding up vertically where my arrows are getting larger and larger and larger here. And so now we do the superposition. So superposition says that if this is our first state of the ball, what's our second state of the ball? It's a sum of these two. And then our third state is the sum of these two. And our fourth state is that sum. And then you could see here that all I'm doing here is that the superposition then says that the way I map out the ball as it's moving through these, it's really a combination of using the parallelogram rule to actually map out how this ball is going to move here. And so what you're seeing here is that this path is not along a straight line, but it's, I don't know how to actually draw this accurately, but what you're seeing here is that you're getting this curved path. So by superimposing both motions, one gets projectile motion, which tells you that you have a curved / parabolic path. By the way, I know that it's common for textbooks to say parabolic. It's actually not parabolic, it's elliptical. It's just that the Earth cuts off part of the path because it's hitting the ground. So what we could say here, just by looking at this picture, right? In summary, we could say that the x motion of a projectile always moves with constant x velocity. In other words, v initial x is the same as v final at any other point. This must be a constant since the acceleration in the x direction is 0. And we know that the y motion of a projectile is always free fall motion. That means that the velocity in the y direction is always changing. The velocity in the y direction always changes since ay is minus g. So I'm always getting the change in the velocity here. So what I want to do here is that, and there is some difference here, and you know, I have been trying to get onto this website to show you an applet, and oh my gosh, it just came up after it's been running for quite some time. So what I want to do here, let me see if I can make this bigger. I can. Let me organize this here. And what I'd like to do here is I want to set you up so that I can, you know, try to make it really clear here. And what you're going to do here is I'm going to use an applet to show the superimposed motions. Okay, so check this out. Let's look at this applet. So what I'm going to do here is I'm going to go in and share my screen. Okay, I'm assuming that you're seeing my screen right now, and what you're seeing here is that I have a blue ball that starts, and as soon as I click on it, look what actually happens. So let's check this out. So you could see that as the ball is moving, it's going up. It's in a state of free fall with these red balls, and then the blue ball is moving at constant velocity. But you could see is that as I superimpose these two motions, I'm recreating this trajectory. And as I'm coming all the way down, you could see how you're getting this superposition of both motions here. And so what we want to do here is that, you know, I want to restart this just only all the way up to the top here. And I want to bring this into our discussion here. And let me go back to my OneNote. And if I paste this guy in here, what you're seeing here is, again, you're getting this superimposed motion here. So if you're looking at this guy, I come here, and then this guy goes right there. And you could see how I constantly am doing this with this superposition here. And so when I'm really looking at this thing, That's what I mean by superposition. But what I want to do here is that this time, instead of showing you that what we just did last time, this time I'm going to put my velocity vectors in this time. So what I'm going to do here is that I want to show the velocity superposition. Okay, so I'm going to erase these lines and then put in velocity vectors now. So now let's go look at the velocity vectors. And you know what? I think I'm going to have to make this bigger to make it clear enough. Okay, so let's go look at this thing here. So when the ball shoots up, note that the length of these vectors, of these guys, should all be the same. So let's go look at this. Okay, but the red should be getting smaller. So then check this out. So if I take my red for this spot right here, and I take my blue for this spot, let's see if I can draw this just right. So this guy's going about this length, so it's going to go from here to here. And then if I look at the red, you can see that the red's going to go from here to here. So the question is, what is the superposition of the velocities? Using the parallelogram rule, you could see that that's the direction of the velocity right there. Now, if I come up to the next one here and I do the exact same thing, you could see I have this one, and then this guy's going to go about right here. And if I do superposition again, you could see that the velocity in this case is changing direction here. And you could see that the x component is getting bigger and bigger and bigger. And I'm thinking that when I get to here, it's going to be really tiny. And the blue is, since it's not changing length here, I think that's a little bit too long. You could see that when I get up to the very top, my horizontal vector here is getting really up like that. So you could see how the velocity vector is actually changing as I go up here. And so you could see that this velocity vector is getting flatter and flatter and flatter, right? You're seeing that the velocity vector is getting flatter and flatter. In other words, it's approaching theta equals to 0 degrees, where angle is measured relative to positive x-axis. And then when you get to the very top, what you're going to see here is that there's going to be one horizontal vector here. And I'm assuming that this is at, how do I say this? At the top here, right there, you're seeing that the full velocity then is only the x direction. So at the very top, our velocity vector, which should be vx squared plus vy squared, and projectile in free fall motion, we know that at the top, that guy is 0. So all of the velocity is in the x direction. And once again, that's really telling us about the superposition of these motions right here, which is pretty phenomenal when you think about that. So these guys are completely independent of these things. Now, there's lots of really fantastic demonstrations. There really is. Unfortunately, to try to do these is not very good. So what I want to do here is I want to show you evidence of this independence of motion. Okay, and so the first one here is really a very, very famous one, is that essentially imagine that you're holding a bullet. So suppose one holds a bullet and a second bullet is shot from a gun. So the very well-known question is, which hits the ground first? And you probably already know the answer to this thing, and you may have even seen the demonstration of it. But what I'd like to do here is that I'd like to sort of like show you videos, because since I really do not have access to really setting up these demonstrations very well. So what I'm really hoping here is that YouTube doesn't come in here and actually start doing the advertisements here. Let me see. Okay, good. Let me go share my screen, the first one with you. So I have 3 that I want to show you. So then check this out. So here we go. Here's the first one. So that's the one where he's shooting. And that's the one where he's dropping. So now he's going to do both simultaneously. And you can see that they both hit the ground. They look like they both hit the ground, even though one has an initial horizontal velocity. I have another one that I think is good here. And this guy's an interesting guy. But what I want to do here is that I want to run what he has, and he has a little bit better version of it. Okay, so check this out.
Video. You can see that they both hit the ground at the same time. And in fact, if we slow it down enough and go frame by frame, you can see that they actually are at the same height at the same time as well. Again, because in the y direction, all the uniformly accelerated motion variables are the same. Wait a second, right before they hit the ground, isn't the one that was...
So you can clearly see what's going on there, right? Assuming that you understood what I was talking about, that what's amazing about this is that these videos absolutely show that the vertical and horizontal motions are independent of each other. And the reason why that is here is that one, right, when you drop one of them, it's just going like this here, right? It's falling straight down. And so the reason why that's independent here is because we know that in this case, there is no horizontal motion. There's only vertical motion that you're actually seeing here, right? But then what he has here is that you saw the video here. What you're seeing here is that now there's a second ball that's shot. And as this thing is shot, there is a superposition of these guys. And when you see the superposition, you're seeing that these two motions, even though this has a Vx that's not equal to 0, it's constantly, the superposition then tells you that these guys can have different motions horizontally, but their y's are completely independent of that x, and therefore you get the same type of ball hitting the ground at the same time. Now, to further stress this thing, there's this thing called what do they call it? I think they call it the hippie jump, if I remember correctly. Right? So then there's the so-called hippie jump in skateboarding. And what you're seeing in the hippie jump here, what you typically find here is that a person is riding a skateboard and they jump over a barrier. And what's amazing about this is that the skateboard remains under this person the whole time, even though the jumper, the skateboarder, actually has a different motion, right? And there's one last video that I want to show you here. Which is just this one guy here. And the thing that you want to pay attention to here, there's another jump, but it's not nearly as clearly. There's this guy that's going to jump over this guy, and he has his legs open. And check this out. Look at the board. You could see that he lands, even though his vertical motion is different, that board stays right underneath him.